Welcome, everyone. Good evening from Malaysia, and at your time, it's probably good afternoon. And for those joining in from Oxford, good early afternoon. I'm calling in from Malaysia, and this is our first lecture of a series of 4 lectures on statistics. And today we'll be discussing on univariate statistics, which is one univariate, variable, and statistics. So we would require you to participate in a way that is anonymous. So no worries. Okay, just give me your most honest opinion on some of the questions that we have for this lecture. My name is Cedric. I am an assistant professor at the University of Nottingham Malaysia, as well as a college lecturer at the University of Oxford. So let's begin. So what's our outline today? We will discuss what is statistics. Okay, why do we use statistics? What's the importance of it in our careers in the medical field? And what's the difference? We will look into some of the parameters such as what is a sample versus population, definitions of common terms, the descriptive statistics such as mean as well as standard deviation, the types of variables that we have in statistics, continuous, they may be categorical as well, and how we present our data in the form of graphs. And finally, we would end off with parametric versus non-parametric tests, what they are. And to begin the session, let's look at the rules of this session. There are questions of true or false. When you see this symbol, I would like you to pull in. You'll see a poll that appears on your screen, and you just have to click true or false. This is for us to understand whether I have explained something right well, so that it helps me understand whether I would need to repeat what I've just said or everything is clear and we can move on. I also had a few of you answering the questionnaire on Google Forms, and it helped me understand your understanding of this subject. So thank you very much for those who have given your answers to that quiz. So let's begin. What is statistics? It's a science of learning from data and of measuring, controlling, and communicating uncertainty. So the variation. So if I ask you what's your height, there is variation. There's bound to be variation. My height is 170 cm. That's not a secret. My age is 37 years old. And so there's variation in age, variation in height amongst people, and the variation might be explained by, for example, the gender differences. So maybe on average, females are shorter than males. So there is the variation in the population, but this variation is explained by the differences in height between genders. So in these, like if we look here, these are 5 people, okay, and we're looking at the height. There's also differences in gender, there's differences in age, differences in race. But we are primarily, today we're focusing on human height. So there's variation, and you can see on average, although not many females are represented here, on average, the females are shorter than the males. So things vary, yes, and they vary because of several reasons. There's the measurement error, in which sometimes we measure and we have a judgment, okay, or there is instrumental error. It's not working very well. So the measurement error, okay, there's systematic error and random error. Systematic error is when the machine consistently give you higher readings. It's not too well calibrated. It's always faulty. Those are systematic error. Or saying your weighing machine is always giving you heavier weights than your actual weight. And random error. Sometimes we have random error, like for example, on that particular day when you're reading the measurement of the height of a plant, your a piece of dust flew by because of the wind, went into your eye, you teared, and because you couldn't see clearly, you gave an erroneous reading. That is random error. It's totally random, very, very difficult to explain. And things vary because of temporal and spatial variation. Some of us grow taller with time, that's temporal variation. Some of us spatial variation, okay? So maybe our confidence vary with the area in on a personal level. If I'm in Malaysia or Singapore, I'm slightly taller than the average person, so my confidence is slightly larger. If I'm in the UK, I'm actually shorter than the average, and actually my confidence level goes down a little bit. That's just an example. It may not be true. I'm just kidding. And also things vary because of genetic and environmental reasons. For example, some of us have certain genes that make us really tall. Some of us eat really well when we grow up, so we might have a height spurt. So that's the environmental reasons. In stats, we are primarily interested in variation that can be classified as two types. The one that is occurring by chance. This is the one that's unexplained by the things that we did not put in the model. Like, for example, we did not consider gender, we did not consider environmental factors in the statistical model. When we analyze it, that's the unexplained variation. But if we put gender, we try to explain the variation in height. That's a explanatory variable. So gender becomes an explanatory variable if we place that in the statistical model. So the unexplained variation cannot be accounted for by the treatment or the explanatory variable determined by you. And the other side is, not surprisingly, the variation that is of scientific interest due to the treatment or the explanatory variable. So this is what you place in the statistical model. So why do we do stats? Stats is a way of measuring, controlling, and communicating uncertainty. It reduces a true or false answer. Okay, let's fill in the blanks and see whether this is true or false. So it reduces the subjectivity due to variation by chance and allows us to describe data in an objective manner. Let's hear from you. True or false? Are the blanks true or false? So you'll see a poll coming in front of you, and I would like you to submit your answers so as to help me gain a better understanding of the way I convey information. Okay, we have half of you polling in. It will be great if everyone, almost 75% perhaps, you can even, if you're listening into this lecture using a phone, you can also do that using the phone, no worries. It should be a window that pops up right in front of you. If not, it's just behind the Zoom window. Okay, great. Let's see what you have. Here I'm sharing my results. Okay, most of you, okay, most of us have 94% have chosen true. That's very good. It reduces the subjectivity due to variation by chance, and we want to describe data in an objective manner because we want to be confident that the variation in height is explained by our explanatory variable. So indeed, statistical tests aim to quantify the effects of what we study and the confidence with which we can generalize about the population we have sampled. We'll define population and sample in a bit. So why do we do stats? As a scientist, we want to study real-world phenomena, say the wildebeest in the savannah, African savannah, and typically, we only study a small sample of the larger group of individuals because if we were to measure, let's say, the weight of all the wildebeest in the population, we'll probably not live to see the data being analyzed because we have to capture most of them. There's a lot of time and effort that goes into it. So typically we are able only to sample a a small number of the larger group of populations. And in such cases, the statistics that we gain from the sample helps us understand the following questions. If I assume that the sample, the smaller number of individuals that I've studied, is representative of the group they come from, what can I tell about the population or the group as a whole? Is it we are assuming that the sample is representative, so what can I tell about the population as a whole? Okay, and the second one is how confident. Okay, the window is blocking what we have here. Okay, so I can't really see how confident we are that the sample is representative of the population. That is the other question that we want to answer, because we want our sample to be random, to be representative. So we need to make sure that we are confident that it is representative of the population. So this is a illustration of what it is in another example. A population of humans, we want to know, let's say, the human height of this population. However, we do not have the resources for sampling everyone here. We randomly select them and we work with a sample. With the sample, we gain what we call the statistic, the mean, the standard deviation, the median, the confidence interval. All these are statistics. They are numbers. And we use the statistics to make inference about the population parameter. So population parameter is actually the population height, the population standard deviation. All these are numbers as well. So statistical literacy is important for critically reading and evaluating scientific studies. As you probably realize from reading lots of papers, we often need to understand what they mean by p-values, t-values, as well as significant differences. It is a powerful tool to use in our own investigation so that you can interpret your data with confidence and present them with authority. What is univariate statistics? That brings the question back to the title. And it is a type of data in which consists of observations on only a single characteristic or attribute. So human height, okay, is one variable. One variable, human height, is a single characteristic. So we are primarily concerned with just one parameter. For example, the age of COVID patients, okay, this is one of univariate, one example of univariate statistics, the age of COVID patients. And this is data that's taken from a paper. We look at the number of individuals, okay, number of individuals against the height on the x-axis. And we can see that the number of deceased are the deceased patients, the ones that have passed away, are older than the ones that have been infected on average. So there is a huge range of age for those that are alive or unknown or infected with COVID. But for those that have disease, these are the ones that are older. Okay. So just to define some parameters, okay, most of them are familiar to you. When we say a population, a set of entities or individuals about which we want to draw a conclusion, but we never really know the true population parameters because we do not have the time and money to sample everyone. Parameter is a number which defines a characteristic of the population. And we have a sample, the entities or individuals which we randomly sample or which we measure to represent the entire population. And finally, statistics, another number, but this time it defines a characteristic of the sample. It's simple to remember: sample statistics and population parameter, so PP or SS. some more definitions. Okay, but this time is a true or false question. Let's hear from you. A constant is a characteristic that stays the same, and a variable is a characteristic that can vary or take on different values. Let's hear from you, okay, with regards to whether this definition is correct. Great. So we have 77% of us are voting. Uh, I strongly encourage you to poll in. Okay, it's just like elections. Yes, one vote might not make a difference, but if everyone has that, if everyone places a vote, it might change the whole election result. All right, great. Thank you very much. It's a simple question. Yes, indeed. What we have here, the definitions are true. Constant is a characteristic that stays the same. And when we say variable, statistical variable, a characteristic that can change. This might be confounded with other definitions. The value is a number. It's not like human height. It's a number representing one of the possible states of the variable. So human height is a variable, but 170 cm is a value of human height. Do not confuse value and variable. So value is 1.87 cm and the variable is height. Great. What is descriptive stats? This is used interchangeably with summary stats, and it includes measures of location and spread. Location is just one number. Okay, spread would usually refer to a range of numbers. As you can see here on the graph, the y-axis represents the proportion of the population, okay, and on the x-axis we see the numbers 0, 1, and -1. So 0 is the mean, okay, and 1 is the one's standard deviation. We'll look at the definition of standard deviation in a bit. But you can see the three different curves, they vary in terms of the mean. The red one has a mean of 0, okay, mu means mean, and the sigma square is a variance, is the notation for variance, and 0.2 is the variance. And we have the green line, the variance is larger now, and you can see, therefore, this curve is flatter. One thing to note is that the area under the curve always equals to 1, because 1 represents 100% of the entire population. All right. So the mean, simple. This is the sum of the values divided by the total number of observations. It's one for which I ask you, what's the mean height of the people attending this lecture? I take all your heights and then divide it by the number of participants, which is 50. Okay, so I add all your heights and divide it by 50. Simple. Median is 50% of the observations lie above and 50% below. So if I ask all of you, okay, to stand side by side from the shortest to the longest, no, to the tallest, okay, shortest to the tallest, and the person who is in the middle, 25th on 26, okay, 25th and 26th position, those two heights, okay, if I add them up and divide by 2, that's the median height of the 50 participants that we have here today. And the mode, most common value, okay, so say some 5 of you are at the height of 171 cm, okay, and 5 of you, but other heights, like for example 174, you only have 3 persons. So for each height, we quantify the number of individuals that have that height, and it just so happened that 171 cm is actually the most common value, so that's the mode. So in a situation for which the distribution is symmetrical, so same on the left side and the right side, then the mode, median, and mean would fall exactly in this vertical line on the x-axis. So the x-axis represents the height. So let's say 170 cm, okay? And if the distribution is symmetrical, we have mode, mean, and median. They are all equal. The values are all equal. Let's look at another scenario. Okay, this is a true or false question for you. Okay, what we have here is an asymmetrical distribution. All right, and I want you to check whether the median, mode, and mean are correctly labeled. So tell me, true or false? Let's hear from you. Thank you very much, and let's share the results. Indeed, majority is false. Okay, what is not too right here, okay, is mislabel. There's a mislabel in the median and mode. This is the correct one. Remember, the mode is the most common value, okay? And on the y-axis, the height represents how frequent we have individuals, how many individuals we have for that height. So the highest peak here, okay, would represent the most number of individuals having that height. So this is the correct one. The mode is the right vertical line. The median divides the line into 50%. If we look under the area, okay, remember the area under the curve represents the percentage of individuals. So this median divides the curve into two equal areas, 50% on the left and 50% on the right. So the median is the second vertical line, and the mean is an average of all numbers that you have to calculate and then put the vertical line there. Okay, thank you very much, and well done to those who have got it accurate. So here we have another type of descriptive stats. Okay, on the graph on the left, we have a different way of representing the different numbers. We have the number here, okay, minus. So the mean is, we have 5 data points, okay, and the number here is 0.8. Okay, we look at the y value. This is the x label is nothing very much. It's just a data point 1, 2, 3, 4, 5. It doesn't mean the actual values are on the y-axis. So we can see that the mean of these 5 values is the horizontal line, and some data points are below the mean and some data points are above the mean. What's important is that if we take minus 1.6 plus minus 0.6 plus 0.4 plus 0.4 plus 1.4, that would give us the mean mu. Okay. So variance is denoted by sigma square. And how we calculate variance? Variance is the sum of square deviation divided by sample size square root. Okay, so what this means, let's by sample size n. Okay, so say the deviations are 1.4, 0.4, 0.4, 0.6, 1 minus 0.6 and minus 1.6. So we take all these deviations, we square them and we sum them. That's what it means by sum of squared deviation. Then we divide it by sample size, that's 5. I say again, we take all these numbers, 1.4, 0.4, okay, we square them and then we sum these and then we divide it by 5. This is the actual equation. The sigma square is the variance, is the sum of the deviation. So x is actual data, okay, actual value of the data. Here is 4.2 minus mu. Mu is, let's say, 2.8, okay, and 4.2 minus 2.8 is 1.4. Okay, so that would, 1.4, we square the value. Then we do 0.4, we square the value, 0.4, we square the value, minus 0.6, we square the value, and minus 1.6, we square the value, and we add them all up. So that's the sum of the squared deviation, and we divide it by the number of samples, 5. The standard deviation, okay, is one for which is the square root of the variance. And we do this because that will give us a measure of the spread in the same units as the mean. The variance has a unit that is the square of the the original parameter. So if it's the variance of height, it will be cm square or meter square. But standard deviation, because we square root the variance, so it would be the same unit. And usually we use standard deviation as a preference. So two samples may have the same mean, but different spread. We can see here they have the same mean, but the data points are very close to the line here. And this data on the right, the data points are very far away from the line. So this is a question from you. Is there something not quite right with the diagrams, or everything is fine? Okay, so if everything is fine, select true. If everything doesn't look quite right, okay, anything that is fishy here, please select false. So what we have here is majority false, but this time we are getting very close to 50-50, just like the Brexit results. And what we have here is a mislabel. As you can see, the variation, okay, is larger on the right. And that would mean the standard deviation should be higher. Standard deviation, the larger the standard deviation, the more variation there is. Okay, because the standard deviation is just the square root of variance, and variance is a measure of variation. So the more deviation there is, the higher the variance, the higher the standard deviation. So there's a mislabel. So well done to those who have spotted it. The answer is false. Standard error is something that you have experienced very much in the manuscripts. Okay, it's the standard deviation divided by square root of n. So once we get standard deviation, we divide it by square root of n. And another less common way of measuring spread is the coefficient of variation. And this measures the spread of a data set as a proportion of its mean. Is often expressed as a percentage. So the answer to one of the quiz is it's the ratio of the sample standard deviation. Okay, you divide the standard deviation by the mean. This is often less used. Okay, I don't see it very much in the actual literature, but this is something that might be useful, let's say, to compare standard deviation with the coefficient of variation between two different genders or heights. Okay, so because the standard deviation might vary when for different genders, the mean also varies with the different genders. So we might use coefficient of variation to divide the standard deviation by the mean. So there are types of variables. We have the categorical is divided into groups, and an individual either belongs to one group or another, or it doesn't, like gender, male, female, but now we have also gender neutral, okay, or we also have other things like small, medium, large in terms of shirt size. So a shirt is either small, medium, or large. And we have quantitative. The variable has numerical values that allow comparison of more or less, and an intermediate value is always meaningful. So in this case, 170 and 171 in terms of height, those are numeric values, but there is also an intermediate value, 170.5 is still meaningful. Okay, although we might not use it that often. So the variables are divided into two broad categories: the categorical, which is subdivided into two more, the nominal and ordinal. And on the other side, the quantitative, which is discrete versus continuous. So what's the difference? The categorical, we don't usually use arithmetic operations such as plus, minus, times, divide, because there's no numbers associated, there's no value. It's just small, medium, large, okay, or gender, like male, female. We can't plus the male to a female, etc. Then we have quantitative, for which there's values, okay, there's discrete values or continuous values, and the arithmetic operations are meaningful. You can add 2 to 4, okay, and quantitative values can be converted into categorical. So let's say a range of height from below 160 is considered the category short. Okay, so that we can everyone that's below 160 cm is considered under the category short, and between 160 to 180 there's this category called average, and we can use that category. So quantitative values such as height can be converted to categorical. So let's delve into the 4 different subcategories. The nominal, as the name suggests, name, it comes from the word name. Nominal variables classify individuals into categories with no ordering, okay? And this individuals either belong to a group or they do not. This is the characteristic of categorical. There's no ordering. For example, species is not as though one species is more than another or better than another. The country of origin as well, there's no ordering. There's no first, second, third, and sex as well. There's no ordering, male or female. Okay, all these are nominal variables. Ordinal variables occur along a scale from low to high, and the order of values has meaning, but the intervals between values are not equal. It can be not equal, it can be equal. It depends on how you classify it. This is another example of categorical. As the name suggests, there is order to it. So this is my example proposed, and I want you to tell me whether it's true or false, okay? An example of an ordinal variable is the finishing place in a race. For example, first, second, third, fourth place. Okay, this is an ordinal variable. So I want to hear from you whether this is true or false. Yes, indeed, the answer is true. Okay, so first, second, third, fourth place is an ordinal variable. We're not interested in the timing of when they come in. Okay, that would be characteristic of an ordinal variable, meaning that the intervals between the values may not be equal. So the first may come in just above the hour, but the second place comes in very close to 3 hours. So there is a large interval or a large gap between the first and the second place. But we're not interested in the time. We're interested in whether you came in first, second, third, or fourth. This must be a very long race for it to reach up to 6 hours. Okay, the discrete variables have an equal interval ordering, and the distance between two adjacent values is the same all along the scale. Okay, this is a quantitative type of variable. So this is equal interval. And let's look at an example, the interval with no natural zeros, and the ratios do not make sense. So interval discrete variable is a subcategory of discrete variable. So in this type of variable, there's no natural zeros. Okay, like dates, there's no zero. When is zero? Maybe some of you use BC or the zero BC, zero AC as the zero, but it's not really a natural zero. It is one for which is defined by humans. And the ratios do not make sense. So you don't usually divide one date by another. Another subcategory of discrete variables is ratio. There is a true 0 point and the ratio makes sense. So for example, population size, if there's 0, that means there's no one, right? And as such, okay, you also can divide population size, 1,000 in country A versus 100 in country B. Okay, some countries, most countries do not have so few people, but I think you get what I mean. Okay, 1,000, what's the relative population size of country B versus A? You can divide the population size by each other. And the continuous one, the fourth type, which is the continuous variables, have intermediate values, or it's possible to imagine more values in between two continuous variables. For example, height and weight. It depends on the instrument, but the example that I've given, 170 and 171, there's always 170.5 and 170.54, 546, okay, etc., etc. There's more. You can always imagine more values between two continuous variables. So the types of variables can be divided into two instead. We are primarily interested in the response variable. So this is the one for which we measure, let's say, the human height, okay? And this is the variable that responds to a treatment or something that we're trying to explain the variation with. And what we measure and want to explain its variation. And the explanatory variable is the other one, okay? This is the one on the usually the x-axis, okay? And there are other terms that are used quite interchangeably for response, the dependent, because it depends on something else, or the predicted, because it's based on predictions by the explanatory variable. For the explanatory variable, that's the independent, okay? Because it does not depend on anything else, and it predicts the response, so it is also known as the predictor. So these terms are used interchangeably. So how best to illustrate the characteristic of a response of the sample and compare them? Okay, that is when we graph our data. When we want to show the characteristic of the sample and compare them, we can examine the data visually. Don't just rely on just the descriptive stats such as mean, median, and mode, as well as standard deviation, variance, etc. Those are values, but it's better to even visualize them. Different types of charts are designed for different types of data. So let's choose the appropriate type of the chart. Let's look at a few of them. This is also known as the box plot, and the X represent the data points along, they vary along the y-axis. So the one at the bottom is the lowest value, okay? One can imagine this is the shortest person, and many of us are average and some are taller than others, okay? So the X are the data points, and the box plot is drawn as such. So this is the black bold line is the median. The median divides the data points into 50% above and 50% below. As you can see, yes, there are 4 points below the median and 4 points above the median. The interquartile range is the box, okay? And so the box is drawn at the 25th percentile and the 75th percentile. This is 75%, okay? And an individual that has 75% of the and sum of the height, okay, you would join. Sorry, this is the data point that is in between the median and the extreme points, okay? And the lower percentile or the lower quartile is the data point that is between the median and the lowest point. So this is the interquartile range. It's the box that is drawn. It is the range between the 25th point and 25th percentile point and the 75th percentile point. And the range is the entire whisker, okay, the whisker. But where do we draw the whisker? The range indicates mean minus maximum, okay, but it does not include the lowest data point down here, because this data point is considered an outlier. It's not really the minimum. It's considered an outlier when it's not drawn within a whisker. So where is the whisker drawn? One might ask. The whisker is always drawn at a data point within lower quartile minus 1.5 times the interquartile range. So what does this mean? Say the interquartile range is 3, okay, the value 3, okay, we take this value and take this value, we minus the upper value minus the lower value, the value 3. Then we take 1.5 times the value 3, that's 4.5. Yes, 4.5. So we use 4.5 as a gauge, okay? Let's say this is the lower part of or this is the lower quartile, this is the lower quartile indeed. And then we minus 4.5. So maybe 4.5 reaches this height here, but it doesn't reach the lowest point here. So we draw it at a data point that's within 4.5 times 4.5 minus 4.5 lower than the lower quartile. Sorry, I'm a bit tongue twisted at this moment. So I say again, we draw the whisker at a data point that is within 4.5 of the lower quartile. So imagine there's a imaginary whisker here, but there's no data point here, so we draw it at the data point that is within this imaginary whisker. And anything that is not within 4.5, okay, will be considered an outlier. Another way of representing a single characteristic or a univariate is the pie chart. And here we see the percentage, okay, the area, okay, of each country: Russia, Canada, China, United States, Brazil, and Australia. All these are very large countries, and we want to look at which country has the largest area, and Russia apparently has 27.3. Okay, it shows quite clearly that Russia has the largest areas among all other countries that are represented on this pie chart. And this is for a categorical variable, the one that is country. Country has many categories, and we compare the numbers in the different categories. It's quite straightforward. Good. And another way of looking at the graph is the frequency histogram. This is one for which the interval variable is on the x-axis. In this case, we look at maybe human height, and we have 160 to 165, 165 to 170, 170 to 175. Those are intervals that we classify ourselves. And on the y-axis, okay, the bar height indicates count, or the number of individuals with that range of height. So we have, let's say here, 10 people between the height of 160 and 165, 0 people from 165 to 170. That's how we look at it. Okay, a true or false question. This represents the density of data. Okay, the area under the curve represents the density of the data. Let's hear from you whether this is true or false. Okay, so frequency histogram sometimes is a smooth curve, okay, instead of one for which it is based on the bars, regular bars over here. But when we say histogram, usually we look at the bars. So one thing I wanted to say that the question on whether it represents the density of the data. Okay, great. Thank you very much. And most of you have pulled in true. The answer is indeed true. Okay, so remember that there is an interval here. Okay, 160 to 165. We have 2 people. So this block here represents the height, and it is quantified by a regular interval. Okay, so the area under the curve represents the density of the data, because the bar are regular areas. It's not one vertical line, it's a bar. Thank you very much. Well done. So majority have chosen true, so the answer is true indeed. So we finish off this section with parametric versus non-parametric, because it leads on to the next section on linear regression, and we look at the difference between parametric versus non-parametric. So first up, what are these tests for? Okay, we want to answer the question whether there is a relationship between the explanatory and the response variable. So remember, we have human height as the response variable. It varies, but we want to explain the variation with, let's say, gender, or let's say the age. Okay, different people have different age. People have different heights. And so if we were to plot this, okay, here we have, let's say, the age, which is on the x-axis, that's the exponential variable. And as you uh, become older, you become taller. That's the y variable, that's the height, okay? At one point in time, of course, you stop growing. Another function of these tests, the parametric or non-parametric, is to understand whether the explanatory variable has an effect on the response. And we often plot this using a bar chart, one for which the x-axis represents two different categories, like for example, gender, male versus female, male on the right and female on the left, and the y-axis is the height itself. So we are trying to explain the variation in human height with gender, and this is whether asking the question whether the explanatory variable gender has an effect on the height. So these are two different types of tests, parametric versus non-parametric. They serve the same role as to try to explain the response variable, okay? Either with a categorical explanatory variable or a continuous explanatory variable. But the parametric versus non-parametric, we often have an equivalent. So the parametric test may be a paired t-test, but there's a non-parametric equivalent, which is the Wilcoxon rank sum test. And we have the unpaired t-test, which is paired up with, which is equivalent to the Mann-Whitney U-test. And we have the Pearson correlation match up with the Pearson correlation. One way analysis of variance match up with the Crystal-Wallace test. You might be experiencing the Pearson correlation very soon in the linear regression lecture, and maybe the one-way analysis in another lecture. And just note there is a corresponding non-parametric equivalent. But what's the difference, one might ask? Let's first look at some of the assumptions of parametric tests. Okay, assumption is something that we need to assume of the data. There are three assumptions: independent and random samples, the data is normally distributed, and there is a homogeneous variance. The error should be equally variable over the range of response. And the first assumption, let's look at independent and random samples. Okay, so this is, let's say we go to this area and we sample the soil 3 times. Similarly, we go to area B, we do the same thing, we sample the soil 3 times for its pH. Okay, my question here for you is this independent random samples. Let's hear from you. So we go to 5 different areas. In each area, we sample 3 times, and each data point, each axis, we consider independent and random sample. Is this a true or false? Is this true or false? Those axes, are they independent and random? So most of us say true. Unfortunately, the answer is false, because the samples from an area A, they are located so close to each other, they might have very similar values. That means the samples are not independent. They are kind of correlated. They might be dependent on each other. They have similar values. And this is a case of what we call spatial pseudo-replication. So when we treat those samples, those 3 values as independent, but they are actually not, that's pseudo-replication. And because it's space related, that's spatial pseudo-replication. So to deal with spatial pseudo-replication, okay, and to make our samples independent, we need to average the multiple measurements of the same area. So we take these 3 measurements and we average them. That's one independent sample. We only have one value from area A, not three values from area A. And then that would be independent. Okay, great. And we have a case of temporal pseudo-application. There are three birds here, Tom, Dick, Harry. We measure Tom's wingspan 3 times, once, and Dick and Harry wingspan. And after a certain time, we measure it again and again. So each individual here, we measure their wingspan 3 times each. And to deal with this, we have to average the measurements of the multiple individuals. So we have to average the measurements, okay, of Tom's wingspan instead of treating those 3 measures as independent samples. They belong to the same individual, so we have to average the measurements of multiple individuals. Okay, great. The second assumption is the normality of data. As you can see here, there's only one distribution that's normal, which is the center one. It must be symmetric, okay, and that is normality, okay. And on the right, there's a positive. On the right, there's a negative skew, meaning slightly tail on the left. That's negative skew, and positive skew is when there's a tail on the right. These are not normal distribution. So only the center one is meeting the assumption of the parametric test. And the last assumption, homogeneous variance, and the error should be equally variable over the range of response. Let's see if this fits the assumption. Are these 2 accurate representations of homogeneous variance? Let's hear from you. So we have majority true, okay, well done. Homogeneous variance means the variation does not change over the range of the response. So as X increases, the variation does not increase. As X changes from male to female, the variation is not different, okay? So the length, the vertical length here of mean A is the same or similar to that of mean B. This is true. This is good. This is good representation of homogeneous variance. However, this is not good. As you can see, as X increases, the variation of Y increases. Similarly, the variation for B is larger than that of A. Great. So what if the assumptions of the parametric test are violated? That's when we use the non-parametric test. Okay, so that's the difference. Parametric tests have the 3 assumptions, and if we check for any of the assumptions and they are violated, then we use the non-parametric test. There are 2 other ways of dealing with the violation of assumptions, which we will not go through it in this lesson, but we can transform the data. Say we have right skewed or left skewed, we can actually transform it by x squared or square root to fit normality. And the final one is generalized linear model. We can fit a non-normal distribution to our data. So these are the step 2 and 3, slightly more advanced techniques, okay? But you can feel free to look them up if you wish to. Usually we just go for a non-parametric equivalent of the test that we are trying to use. All right, summary. We have looked at what is statistics, okay? Statistics is a way of quantifying data in an objective manner, not subjective. Why do we use statistics? We want to be confident with our results, to summarize our data, to quantify the mean, the standard deviation. We look at sample versus population. We never know the true population parameter, therefore we need to sample and gain the statistic, the value of the sample. And definition of some common terms, okay, such as value, variable, constant, and we look at some descriptive stats, mean, mode, okay, and standard deviation, standard error, variance. the type of variables, we have ordinal, we have continuous, we have nominal, we have finally the discrete. Okay, so those are the 4 subcategories under categorical versus quantitative. And we look at how best to show our data with frequency histogram, with the pie chart, okay, and the box plot. And finally, the difference between parametric versus non-parametric. Parametric has 3 assumptions, and if any of the assumptions are violated, we should be using the non-parametric test. Thank you very much for listening, and I hope you enjoyed yourself and gained a better understanding of statistics. And so, yes, we have came to the end, and I'll welcome any questions. I guess we'll pause here for any questions you might want to type. I might just have time for a few. A Likert scale. A Likert scale is when you ask a question to someone, to what extent do you agree with this statement? And you have 1 which is I completely disagree, and 7 is strongly agree. So that is an ordinal. That's an ordinal type of variable because it's 1, 2, 3, 4, 5, 6, 7, and that is ordinal type of variable. Can we measure homogeneity? Yes, there is. Other than looking at the graphs or the charts that we have seen earlier, there are tests that test whether the variance are equal or not. That's the Levene's test of variance, and do look it up. Levene, Levene. I'll just type it in. Okay, test for homogeneous variance. You can officially test it. And I think there is a short reminder to fill in the feedback to this session, as well as the post-lecture quiz to really solidify what you learn. Please explain the concept of pseudo-replication. Very good question. Pseudo-replication is fake and replication. So replication is fine. So what we mean by replication, we measure heights of independent samples, like my height, your height, someone else's height. That's true independent replication. That's replication. Okay. But if I measure my height 3 times, your height 3 times, Becky's height 3 times, and we take those 3 measurements as representative of 3 different people, which is not the right thing to do, or it's quite silly, then we commit the mistake of pseudo-replication. It's a fake replication. It's not real. Okay, it's okay to measure my height 3 times. Okay, but if you treat it as the height of 3 different persons, that's pseudo-replication. But if you measure my height 3 times, okay, that's repeated measures, because you're doing the right thing. You measure my height 3 times just to be sure, then you take an average of my 3 measurements. That's fine. That's the right way to do it. But if you treat them as 3 different people's heights, that's pseudo-replication. I hope that's clear. Okay, great. Thank you very much. Lovely to see all of you. And I understand on Fridays it's probably a holiday in Palestine, if I'm not wrong. So yes, enjoying your long weekend, and happy Chinese New Year from Malaysia. And good to see all of you, and enjoying yourself tomorrow as well. Thank you. Thanks very much.